Okay, so today we will solve GET 2023 mathematics questions from linear algebra. This is question number 22. This is 1 mark question. So what is this question saying? Let T from R4 to R4. So this is a linear transformation, and the null space of T is the subspace of R4, which is given by this, right? And saying that if rank of T minus 3i, which is 3, where I is the identity map on R4, then we have to find the minimal polynomial of T. So 4 options are given. Option number A is the minimal polynomial will be x into x minus 3. Option B is minimal polynomial will be x into x minus 3 whole cube. Option number C is minimal polynomial is x cube into x minus 3. And option number D is x square into x minus 3 whole square. Okay, so let's solve this one. Also, in order to solving the question, you can look at the for NPTEL reference. This is the NPTEL reference. Okay, so let's solve it. So whatever definition and results needed in solving the question, I will write it whenever it will need. Okay, so what is null space of T is given by this. So let me denote this is null space of T. This is called null space of T. What is this? This is by definition basically all such vector in V such that TV equals to 0, right? So what it is given, null space of T, here it is given that this is a subset of R4 such that 4x1 plus 3x2 plus 2x3 plus x4 equals to 0. Okay, so let's find what will be the null space. So this equation is given 4x1 plus 3x2 plus 2x3 plus x4 equals to 0. So from here we can write x4 in terms of this, right? 4 minus x1 minus 3x2 minus 2x3. So as it is only one equation is given, so we can write x4 in terms of x1, x2, x3. So then we can write this, then null space of T, you can put it here, right? x1, x2, x3. In x4 you can write in it is this minus 4x1 minus 3x2 minus 2x3, where x1, x2, x3 are x1, x2, x3, these are real numbers. So then what it will look like, so you can write x1, you can take common 1, 0, 0, minus 4 plus x2, 0, 1, 0, minus 3 plus x3, 0, 0, 1, minus 2, right? And where this is as early x1, x2, x3 are real number, right? So here you can check that this, let me call this is v1. What is v1? 1, 0, 0, minus 4. v2, 0, 1, 0, minus 3. v3, 0, 0, 1, minus 2. So one can easily check that these three vectors are linearly independent. So these are v1, v2, because you can always check that in the first component only v1 is non-zero, but in the second component v2 is only one non-zero, and the third component v3 is non-zero. So one can easily check that these are linearly independent. Right? Okay, and there belongs to the null space of T, right? Because null space T is basically the linear combination of these three vector. So they will generate this null space. So null space of T is basically a span of these three, a span of V1, V2, V3, right? So null space has dimension also 3. What is meaning by these are in the null space? So by definition this is the meaning that Tv1 is 0, right? Tv2 is also 0, Tv3 is also 0, right? So from there you can easily see that Tv1, you can write 0 into V1, Tv2 you can write it 0 into V2, and Tv3 you can write it 0 into V3, right? And V1, V2, V3 are linearly independent, so they are non-zero vectors, right? So these three equations are telling that V1, V2, V3 are the eigenvector, right? Eigenvector of T with eigenvalue 0, right? Why? Let me give the definition. If someone has any doubt, let me write the definition. So definition, what is a vector, a non-zero vector V, suppose this is in the vector space V, is called an eigenvector of a linear operator or transformation, linear operator T with eigenvalue lambda if Tv equals to lambda V, right? It will satisfy. V is in the space B. So this you can also write, this is same as, right, T, you can take it this side, minus lambda V is 0, right? This is same as this. And so what is meaning by this one? So here it is basically the identity operator is there. So let me write it explicitly, means lambda into identity V is 0, right? So it is the where V is non-zero. So lambda is called an eigenvalue with eigenvector V if it is satisfies this equation, right? So which is same as saying that T minus lambda is not invertible, right? Because V is in the null space of T minus lambda, so it is not 1 1. So a non-zero vector which sends T minus lambda into 0 vector, which is the meaning that T minus lambda is not invertible, right? So this is the definition. So what we have got, that V1, V2, V3 are the eigenvectors of T with eigenvalue 0. Okay. So from this one we have got this one, and now we use this one, right? Rank of T minus 3i equals to 3. So let's see what we have got from there. Note given that rank of T minus 3 identity 3i is 3, right? So what is this saying? So T is a linear transformation from R4 to R4, right? And identity is also a linear transformation from R4 to R4. So T minus 3i it is also a linear transformation from R4 to R4. So rank of 3 is given. So rank of T minus 3i. So this is same as the dimension of the range space, right? Dimension of the range space of T minus 3i. So this is the definition of the rank, right? Dimension of the range space of T minus 3. And so this is 3, but T minus 3i is a map from R4 to R4, and it has dimension of the range space is 3, so which is strictly less than 4, right? Because dimension of R4 is 4, so which implies T minus 3i is not onto, right? Because its range has dimension 3, but it is a map from R4 to R4, which has a dimension 4, and it has in range space of T minus 3 has a dimension 3. So this is not onto, and as this is finite dimensional map from R4 to R4, this is a bounded linear operator, which implies T minus 3i is not invertible, right? Because it is not onto means not bijective, so it is not invertible. So what we have seen earlier, that if T minus lambda is not invertible, it's saying that lambda is an eigenvalue of T, right? So which implies that from that result, so what we have discussed above, from there we get 3 is an eigenvalue of T, right? So 3 is so we get, so earlier we have got 0 is an eigenvalue of T. Now we have got 3 is also an eigenvalue of T, right? So let V4 be the corresponding eigenvector. Let V4 be the corresponding eigenvector of T. Eigenvector of T means what is saying that T V4 equals to 3V4, right? And so for corresponding to 0 we got 3 eigenvector, right? Corresponding to 0 we get V1, V2, V3, these 3 eigenvector, and corresponding to V4 we have get this eigenvector V4, right? Because 3 is an eigenvalue, so it has an eigenvector, we have called it V4. And so there is let me record one also one result also. So suppose if T is a linear operator, if T is a linear operator, so eigenvectors corresponding to two different eigenvalue are always independent. So what this result is saying, so suppose let v1 be eigenvector let's say w1, t w1 equals to some lambda 1 w1 and t w2 equals to lambda 2 w2, and if lambda 1 not equals to lambda 2, then this result is saying that w1 and w2 are linearly independent. Right, so we'll use this. So for 0 we have got what we have got, these three eigenvector v1, v2 and v3, and corresponding to 3 we have got eigenvector v4. So as 0 and 3 are different, so v4 is linearly independent to all the 3. So therefore, using the above result, we can say we have that v4 is linearly independent to this v1, v2 and v3, all of 3 vectors, right? So we have, therefore we have got 4 linearly independent vectors. So we get v1, v2, v3, v4. This set is linearly independent. And note also that all 4 are eigenvector of T. Note also that these 4 vectors are eigenvectors of T. And as T is a map from R4 to R4, and we have got these 4 are eigenvectors, and so this has, so they are the basis of R4, right? So we have got a basis of R4 which are the means, therefore we have got a basis of R4 which are consist of eigenvectors of T. So from here we can use a one result that a operator T is diagonalizable. Now let me take one result. That T, which is a T is a linear operator. On V, then T is diagonalizable if and only if the, so not if and only if there is a basis for V for which each vectors of these are vector of V, each of them of which is an eigenvector of T. right? So what this is saying, that T is called diagonalizable if we can find a basis for the vector space B which are consist of the eigenvectors of T. And what we have got, this is saying exactly the same thing, right? We have got a basis for R4 which are consist of the eigenvectors of T. So therefore our T is diagonalizable. Therefore T is diagonalizable. Right. So we got that our linear operator is diagonalizable. So what is the, what we have to find? We have to find the minimal polynomial, right? So here we can also use one more result, that if a linear operator is diagonalizable. So let me write result. So T is diagonalizable if and only if the minimal polynomial for T has the form, so P of some x, it will look like x minus c1 dot 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 x minus ck. So means the minimal polynomial factors into linear factor, right, where c1 up to ck are distinct elements on the field, or the vector space is over field of some field, right? Distinct elements of field where V is the vector space of R. So it's saying that T is diagonalizable if and only if the corresponding minimal polynomial will be factored into linear factors. So what we have got, right? So that, so we will use this theorem. So as T has two eigenvalue, two eigenvalue 0 and 3 with corresponding eigenvectors are v1, v2, v3 and v4 respectively. Right. So how the minimal polynomial look like, right? So it can, so the minimal polynomial, therefore, so what will be the characteristic polynomial? So then the characteristic polynomial will be, so the minimal polynomial will be the linear factor, right? And it has two different eigenvalues, so 0 and 3. So therefore the minimal polynomial will be x into x minus 3, right? So let me write it. P of x equals to x minus 0 corresponding to eigenvalue 0 and x minus 3, because it cannot have more power, right? Because it will be linear factor. So therefore minimal polynomial will be x into x minus 3. So you have got the minimal polynomial for the linear transform of T is x into x minus 3. So therefore which option is correct? Option number A is correct. Therefore Okay.